Referring back to topic 1.1, where we outlined the 5 different major requirements for a battery management system, we're now ready to look at requirements 2 and 3, which have to do with protection of the battery system and the occupant for that matter, and interface between the battery management system and the application. And in my mind, I'm of course always thinking of a vehicle application. These are in no means the primary focus of this course, and in fact, over the next several pages, uh, this is all we're going to look at them. So, about 4 pages of notes dedicated to these 2 topics. They're important topics, but they mostly have to do with the electronic design, which is not my focus, and some of the communication aspects between the battery management system and so forth. It's not the control aspects, which is what the course really hopes to focus on. So I want to bring them up, though I don't want to leave them out because they're important design considerations whenever you're building a BMS. And I want to at least give you the ideas of what to watch out for and what to think about and how to think about designing protection. I'm not going to tell you how to do it, but at least what to think about. So topic 2 is protection. Your battery management system needs to provide monitoring and control to protect cells from out of tolerance ambient operating conditions and the user from consequences of battery failures, however that happened. Now we can pretend that lithium-ion batteries are all very benign and so forth, but that's kind of silly. Anything that stores energy is dangerous. Gasoline is dangerous, a flywheel is dangerous, a battery is dangerous. Energy is, if released in an uncontrolled form, is very dangerous. So is gasoline more dangerous than a battery cell? Hard to say. We have a lot more experience with gasoline-powered vehicles, more than 100 years now of experience in how to manage that risk, and we have far less experience in how to manage a battery risk. But in either way, they're dangerous, and so we do have some knowledge of how to manage the risk of the danger inherent in a battery, and that's what we're going to talk about a little bit right now. So if energy is released in some uncontrolled way, maybe a short circuit or physical damage, if you are in an accident and the battery pack got crushed, or whatever, can have really serious consequences. In a short circuit, the automotive battery cells have such low resistance and such high capacity that hundreds of amperes can develop in microseconds. And so protection circuitry to shut this down must act quickly. Fuses, as we'll talk about in a moment, are one possible way of shutting something down, but fuses don't always act quickly. So this is not a trivial problem. This is a significant problem, but just not one that I intend to focus on too much. Different applications and different cell chemistries require different degrees of protection. A lithium-ion cell failure can be very dangerous. There could be an explosion or a fire. And in an automotive environment, protection is absolutely critical. You just can't get away without it. In a cell phone, that's serious. We've seen all pictures of cell phones that have caught fire. Most people, though, when they're holding their cell phone and it's on fire, they will just drop it and they'll be fine. If it's in your pants pocket, that might be a different story. But if you're inside of the steel cage we call an automobile and it catches fire, that's a much more serious kind of situation. So we have to be very cognizant of the danger that is possible and what to do about it. So we need to think of a number of things. What happens if there is more current than I designed for during charging and discharging? What happens if I detect a short circuit in one of my cells because my cell has failed for some reason? What should I do if there's an overvoltage or an undervoltage situation? What should I do if the temperature is higher than I would like for operating, or the temperature that I develop over time gets too hot? What should I do? The last section we looked at isolation resistance if isolation is broken. What should I do if I detect abuse, that the limits of operation that I provide to the application are not obeyed, and that there's too much current drawn and things like that? What should I do if there's physical abuse, if there's some damage happening? So we have to think about these things, and we need some kind of way of sensing whether these undesirable events have occurred. And it's best if we have redundant sensing to determine if something undesirable has occurred. So some kind of a fallback protection path should be implemented. These pictures try to show this graphically as an idea. And so the first picture here shows on the horizontal axis battery pack current magnitude, so between 0 and maximum, and temperature over some range. And in the corner, in the right corner, top right corner, we have this red area is the failure zone. And this is just a cartoon. This is not the actual picture the way it would look, although it might not be too different. But you have a failure zone, and I want to stay out of that failure zone at all costs. I can't have current that goes out there, can't have temperature that goes out there. So, to be somewhat conservative in the design, we don't simply say that the red is failure, everything else is okay. We have a safety margin. And so we have a failure zone here, but then a safety margin and a safe operating zone. So the green, I could actually operate outside of that operating zone. I could operate in the white area, the safety margin area, and I would be fine. But I choose to constrain the operating zone to give me this margin. And then, whenever possible, I use multiple devices to protect from getting into that failure zone. And you can see that to get from the green to the red, I have to pass through at least 2 blue solid lines. And each one of those solid lines indicates the activation threshold for some safety device. So I might have a thermal fuse that says anything below a certain temperature is okay, anything above the temperature is not okay. And that thermal fuse actually blows. It's a one-time use thing. When it gets too hot, it just completely disconnects. That's a standard fuse. But that by itself would not be enough, because I could still operate out here and the thermal fuse would be okay. So I need something else at minimum. So we have this electronic protection. Now, usually what I mean there is that we're measuring current with our battery management system, and our battery management system detects, oh, the current is much larger than it should be, and it can take appropriate action, if necessary, shutting off the battery pack by opening the contactors. So with these 2 lines alone, that line and that line, if I cross either one of them, or if I don't cross either one of them, I never get to the red zone. If I do cross one and not the other, I might be okay, I might not be okay. But as long as I activate a safety mechanism when I cross one of them, then I'm okay. But suppose I have a failure, that my thermal fuse doesn't quite work for some reason, or my electronic protection doesn't work because my battery management system code froze, heaven forbid. We have a third device here, this resettable fuse, which is a different type of fuse technology, which is different from a thermal fuse. It actually opens the circuit when it gets too hot, but when it cools down, it closes the circuit again. It's a slightly different mode. It has a different behavior. So now you can see that for me to get from the green line to the red area, green area to the red area, I would have to cross 2 barriers at minimum. So there's a redundancy built in. So even if one of my protection mechanisms fails, there's always at least one more as a backup to prevent this failure. So that's just good design practice. We can think of something similar for voltage limits. Here the voltage operating zone might be maybe 2 volts to 4 volts, something like that, and temperature between some low temperature and a high temperature. And the red area is the failure zone, and whenever possible, I'd like to have at least two limits here. In this picture, we see that that's not the case all the time. So you might design other protections in there to make sure that you're okay. But electronic protection saying if the voltage is too low, I open the contactors, or if it's too high, those are protection on the battery side. But if the voltage is too high, it probably means I'm charging. And so the charger could also have its own limits to say, whoa, this battery is getting overcharged. I'm going to open up my own contactors and make sure that I spare things. And again, we could have like a thermal fuse to protect us against an over temperature. Those are things to think about. This is not a very prescriptive design methodology here. It's more of some advice for what to think about when you're designing protection for a battery management system. We'd like to have all kinds of protection. That adds cost. It usually adds some element in the current path, which adds resistance, and then so power losses and so forth. So we have to be careful not to go crazy, but we do want to operate safely. So the protection devices we talked about, things like a thermal fuse, which opens a contactor perhaps, or opens the fuse itself when the temperature is too big. Conventional fuse may not act quickly enough, and that is a big deal. These short circuits can develop in milliseconds, and a conventional fuse may take seconds to act, and that the damage might be done by then. So this here is a big question mark that requires a lot of testing and maybe a different device there. And active fault detection, which is electronic monitoring, maybe the BMS main processor itself, or maybe some other electronics on the side monitoring for fault conditions and taking response. So that's all I have to say about protection. The next topic has to do with charger control for how we charge a battery pack. Battery packs are charged in at least two ways. One of them is random charging, and by that I mean we're driving down the road and the user taps the brakes and we have an opportunity to recover some energy, and we do so and charge the battery pack a little bit. We call that regenerative braking. This is not something that the battery management system schedules in any way. The battery management system has no idea this is about to happen. Most of the time the user doesn't know it's about to happen either. Maybe not quite true. So the user hits the brakes, we get some charge. This is random and unpredictable patterns. And the way we control this from the battery management system is by telling the inverter, the motor controller, at any point in time, this is the maximum regeneration or charging power that I will permit you to put into the battery pack right now. And then we update that power limit on a very regular basis. So the inverter then is what is in communication with the vehicle controller and determining how much of the braking is done by friction brakes and how much is done by regenerative braking. And together they figure that out such that the power limits that we dictate are not broken, and so we don't overcharge the battery. That's how we can control that. So we're going to look at power limits. It's going to be the topic of Chapter 6 and part of Chapter 7. We'll mention it later in this chapter also, but that's kind of a big deal. Another way that a battery pack is charged, though, for some types of systems like electric vehicle plug-ins and extended range vehicles, they have operating modes when the vehicle is actually plugged into the grid and it's not driving. So that gives us a lot more control second by second over exactly what's happening, because we can communicate with the charger and be much more prescriptive with what the charger should do. So we can control the charger current or power or voltage. We can do some battery pack equalization, which we'll talk about in Chapter 5. The type of charging that we often do is something like constant current charging up to a certain voltage, or maybe constant power charging up to a certain voltage. And then we might hold the voltage constant, or we might do other things. There's a number of exotic methods possible, but the idea is to charge as quickly as we think is safe and practical up to a certain voltage, and then taper it off at that point to fill it up the rest of the way if we have the opportunity. I've already mentioned a number of times lithium-ion cells should not be charged at low temperatures, so we might need a heating system if we're doing this. Before we leave the charging, this is very little to say over something that would actually probably be someone's primary job responsibility, to build chargers and so forth. I want to at least give you an appreciation for the energy and power that's required when recharging a vehicle battery pack, and basically the amount of energy that you're pumping into your gasoline tank every time you go to a gas station. So this is our small print. Passenger vehicles, kind of a normal size, not too big vehicle, requires about 200 to 300 watt hours of energy per mile traveled. And I know that's an awful use of units, but that's what people use. So they use metric and the imperial units together. Suppose we want to have a 300-mile range in our vehicle, something like a Tesla Model S. And then we would need somewhere between a 60 to 90 kilowatt hour capacity, just multiplying 300 by 200 and 300 by 300, to achieve that. And just kind of a double check, yep, the Tesla Model S has an 85 kilowatt hour battery pack on the 300-mile range version, and there's probably a little bit of buffer space there, so the Tesla is operating a little bit below 300 watt hours per mile, just based on this rough math. So that's about right. We want to go to a charging station, I almost said gas station, and we want to charge in about 3 minutes. That's what we're used to. If we were to do that, that would require a power transfer rate of 1.8 megawatts. This is absolutely enormous. Yes, it's technically possible, but you're going to require wires, either extremely high voltages, or you're going to require extremely thick wires to carry that kind of current, and you're probably not going to be able to lift the cable. So it's not feasible at this point to even think about charging in 3 minutes, although 15 minutes might be getting close to something that's actually pretty feasible to do in a fast charge situation. So we're not too far away, but 3 minutes is a little bit unrealistic, I think. To give you an indication of what is presently done, what's a little bit more practical, the wall socket in your house is usually a 15 amp rated circuit, maybe a 20 amp in some cases, about 110 volts. And if you multiply those out, you get roughly 1.5 kilowatts. That's a hairdryer. That's a pretty big hairdryer. So 1.5 kilowatts versus 1.8 megawatts. That is 1/1000th of the power capability of charging in 3 minutes. So it's going to take about 3,000 minutes or more to charge on just a regular 110 volt AC circuit. So it would take about 40 hours to 60 hours to charge that battery pack on that circuit. That's just not going to work. That's not going to be okay. So if you have a small plug-in hybrid, maybe a 10-mile range or a 20-mile range hybrid, you could probably get away with a 15 amp, 110 volt circuit, and that would probably charge enough, rapidly enough for most people. But that's not going to be enough for an electric vehicle that's used regularly. So electric vehicles usually use something much beefier than that. So let's consider a 30 amp circuit, 220 volts AC. This is a dryer circuit. Your clothes dryer runs off something about that size. That's a 6.6 kilowatt service, and that would charge your battery pack in about 10 to 15 hours, which is much more doable. If I drive around all day for a few days and I deplete my 300-mile range, and then I plug in at night, usually I'm at home most nights between 10 and 15 hours. And so that would be sufficient to recharge all the way, or at least most of the way. This is called a level 1 charger. This is called a level 2 charger. And there's things called level 3 chargers that are not quite as well defined, but level 3 could be used for fast charging, something more along these lines. But these are what you would expect to find in a home. And the Tesla even offers an option where you can have 2 of these level 2 chargers in your battery pack. So you can basically charge at about 13 kilowatts using your house circuitry. You just have to have an electrician add 2 services, 2 6.6 kilowatt services to make that possible. So with the Tesla then, you could bring your charging time of your battery pack down to between 5 and 7 or so hours, which is very reasonable if I'm at home and charging overnight, and I could do that any night that I wanted to. And if I'm driving on the road, then I would need a faster charger, maybe a level 3 charger, probably not 1.8 megawatts, but something that's quite a bit more than the small number of kilowatts, maybe 200, 300 kilowatts, something like that, in order to charge the battery pack more quickly. So the limitation is partially the limitation of how quickly the cells can accept the energy. And so we'll talk about power limits of cells in chapters 6 and 7, but for most applications, that's not the bottleneck. The bottleneck is the service itself, and that's what I can get in my house. And that's not enough to charge quickly. So I'd need to have a enormous service to charge that quickly. Probably not, but something like that. Maybe a couple hundred kilowatts to charge a battery pack quickly. Have a student. We live in Colorado Springs. If you're a remote student, you can look that up on a map and see where we are. We're about 60 miles south of Denver. I have a student who owns a Tesla, and he's driven from here all the way to Los Angeles and back. There's enough supercharging stations for him to do that, and he thought it was just fine. So that's kind of neat that the infrastructure is getting developed to make electric vehicles, pure electric vehicles, actually feasible. All right, enough of that sales pitch. Another thing a battery management system needs to do is to communicate with other components in the vehicle, and principally the vehicle controller and the inverter and so forth. And that's usually done on a serial bus that's called a control area network, or a CAN bus. That's the industry standard for onboard vehicle communication, and it's so standard that most microcontrollers nowadays have the option of having that built in to them, so you don't have to do any tricky programming. You just have to put some numbers in a register of your microcontroller, and it will handle the rest to send your message to some other hardware element on the bus. The CAN bus standard is not the fastest standard on the planet. It's designed instead to be robust in a very harsh environment with a lot of electrical noise and magnetic interference and all that kind of stuff. So there's redundancy and so forth on the signal and rebroadcast. All that kind of stuff is taken care of for you, so that if you say, send this message to that device, it gets there. It's a 2-wire serial bus, so there's not a lot of wiring needed. That's important. As we've mentioned before, wires are expensive and connectors are expensive. And originally, it was designed to network together intelligent sensors and actuators, and there's 2 baud rates, data rates that are used on the same bus. There's a high-speed rate of about 1 megabaud, and by the way, this is variable. This is not fixed in stone, but roughly speaking, you can do about 1 megabaud. And those are used for critical operations like engine management and stability control and anti-lock brakes and all that kind of stuff, motion control. And then there's a lower speed, lower priority operational mode for about 100 kilobaud for simple switching and control of lighting, so turning lights on and off, putting power doors on and off, and windows and mirrors and instrument displays and things like this. The protocol is a series of bits, and it defines how to address different devices on the same shared bus, the transmission speed and the priorities, the sequences, the error detection and handling, the control signals. This here is one data frame, so we have a 1-bit start of frame signal, and either an 11 or 29-bit address of the recipient of this message, a 1-bit always forget what RTR stands for. It's request to something. I want to say receive, but I don't think that's right. There's a 6-bit control field which says how to interpret the data, and there's 0 to 8 bytes of data. That's the actual message that you're transferring. Everything else is overhead. There's a cyclic redundancy check to see if any of your data got corrupted and needs to be retransmitted. 2-bit acknowledgments and a 7-bit end of frame marker so that the other devices on the bus know when it's okay to start transmitting their own information. So the data frames are transmitted sequentially over the bus, and if anything is corrupted, it's not acknowledged, so it has to get retransmitted and so forth. So it's just a robust serial communication standard that is used, and you can look up CAN 2.0 on the internet to find out more information on the particulars. Another feature that is required of a battery management system is a logbook function, and this is an electronic storage of interesting events. And most often they're going to be events that are unexpected or maybe out of tolerance or something like that we want to record for possible warranty purposes or diagnostic purposes. For warranty, an example would be if I told the vehicle controller you are allowed to use 10 kilowatts, and for whatever reason the vehicle controller drew 30 kilowatts. Well, the vehicle controller is at fault, not the battery management system, if that causes damage. And I want to put that in the log so that we can then figure out who pays the warranty claims when the battery fails. Diagnostic purposes, something went wrong. Well, what is the state of the battery management system when that went wrong, so I can maybe go back later and try to reconstruct the sequence that led to that problem and understand it better so that we can control around that better in the future. So we have atypical events, abuse events. We would probably want to store something like a code that indicates the type of abuse, maybe an out of tolerance event or an over voltage event or over current or over temperature, something like that. So what is the type of the problem, and then the duration of the problem, and the magnitude of the problem. So how much out of tolerance, or how much over voltage, or how much over current, and so forth. So there's kind of like 3 pieces of information that we might want to store for these atypical events. Other diagnostics that we might want to store include the number of charge and discharge cycles completed. So we have an indication of age, some state of health estimates at the beginning of each driving cycle, and anything that you think of. Somehow we store this in a history chip, so a flash memory or an E2 PROM or something, and then we would download it from the battery management system into a computer for analysis when required. I haven't ever seen this implemented. I've thought for a long time that this would be a great idea, though. There are some chip makers that make things called silicon serial numbers, and they're just little chips. They're about the size of a transistor, not very big. But inside of each one of these little chips is burned a unique number, a 64-bit number, and it's unique. And if I attach one of these serial number chips to every module of the battery pack, that would allow me to permanently identify that module, even if for some reason I swapped it out midlife and swapped something else back in or whatever. So, the serial number could help keep track of what data really belonged with what component in the battery pack. Again, I haven't seen that implemented, but I'd like to. I think that would be a nice feature. So the final thing that we talk about in this section is again on reporting and so forth, is reporting back to the vehicle an estimate of how much range is left based on the current status of the battery pack. How far can I drive before the battery pack energy is depleted? And this is proportional, or maybe that's even too strong. It's related to how much energy is presently stored in the battery pack, but it's also heavily influenced by other things that we have no control over, such as the vehicle characteristics themselves. So how many watt hours per mile does it take for the vehicle? If you tell me what that is, and I tell you how many watt hours are available, you can do that calculation. That's easy. But what are those characteristics, and do they change? Is the vehicle being driven gently or aggressively? Usually that has some impact on range. Are there a lot of hills? Is there a lot of wind? Um, Things that are like disturbances that would have some impact. Is the operator using the air conditioning right now versus not, because that can be a huge power draw? Is it warm out? Is it cold out? Because that influences the temperature of the battery system and other components of the vehicle and how well they operate and so forth. So there's just an awful lot of uncertainty in calculating vehicle range. And at present, it appears to me that each automotive OEM is going to have their own range estimation algorithms. And so my focus in this course is not on kind of these fancy things to estimate range, but rather on, can we identify the more primitive quantities that would be needed by a range estimation algorithm or a life estimation algorithm or something like that. So can we estimate how much energy is available in the battery pack? Because if the vehicle computer knows the vehicle characteristics, how the vehicle's driven, maybe the GPS environment, the temperature outside, all it needs from the battery pack is how much energy is available to incorporate that into its own algorithm to figure out what range is. So that's our focus. Very primitive things like how much energy is available and how much power is available in the battery pack, and let the user compute the more application-oriented results instead. So that concludes the requirements 2 and 3. We now move on to requirement 4, which has to do with the state estimation. And our next topic then is looking at state of charge estimation.